थोडं 4-5चं बफर ठेवा, 4-5चं बफर ठेवा.
झाले 99 झाले.
हा, एक अशोक सरांना जॉईन होत असतील तर. Sir, we can start now. Purandare sir.
Okay, sir. We'll start. Good evening to all the participants. I welcome you all for this 6 days workshop on spectral interpretation. This workshop is organized by Siddharth College of Arts, Science and Commerce. I give you some brief introduction to our college. Siddharth College of Arts, Science and Commerce was founded by late Bharat Ratna Dr. Babasaheb Ambedkar in the year 1946 under the People's Education Society. This was the first college to be established under the People's Education Society. The motto, earn and learn. The students were encouraged to take education while working, those who were doing jobs at that time. So with this brief introduction, sir, nice, join. Hello. Hello. Principal sir, join sir.
Nice sir, nice. दिसत नाही.
Okay.
You carry on. Meeting room मध्ये असतील एखाद्या वेळेस.
This workshop is mainly concerned with the spectral literacy. You will find that students after doing graduation as well as post-graduation, when they join various laboratories, including academic laboratories or industrial laboratories, their chemical analysis is not complete without the knowledge of spectral interpretation. So by keeping this in mind with the same, this workshop is organized and this will be covering various spectral techniques which are quite widely applicable, like ultraviolet spectroscopy, infrared spectroscopy, nuclear magnetic spectroscopy, and mass spectroscopy. So this workshop will first cover the basic theory involved in IR and NMR as well as mass spectroscopy. Further, the advanced topics will be also covered, like first order spectra, various systems of NMR spectra like AMX, ABX, then significance of what is coupling, constants, chemical equivalence, magnetic equivalence. This will go further to two-dimensional nuclear magnetic spectroscopy, like correlation spectroscopy called as COSY, then heteronuclear spectroscopic technique, NMR technique called as heteronuclear correlation spectroscopy. So all these aspects will be covered, and the most importantly, along with the theory, there will be lots of spectral interpretation. Right? So various spectra of the compound, single compound were compared, and the conclusions derived from the individual spectra is then correlated, and how to arrive at the final structure of the compound. It's a very skillful job. So all these aspects will be covered in this 6 days workshop, which is held online. Now I would like to introduce, I'm very much pleased to introduce Dr. Nandakishore Chandran sir, who is the associate professor in Siddharth College, as well as he is the head of the department of chemistry. He has cleared various national level exams like NET, SET, GATE with research fellowship. Importantly, he has received his PhD from Oxford University, and his entire PhD program was sponsored by central government. He completed his PhD from Oxford University. So with that exposure from Oxford University, I think he's the right person to have this workshop, introduce to our students various aspects of spectral interpretation. Now, with this brief introduction, I request Dr. Nandakishore Chandan sir to start his session. Okay.
Yes, sir. Thank you very much, sir. It's a kind request to all participants. Kindly mute your mic to enjoy this lecture, because some point we may not aware about our mobile mic. So make it sure it should be always in a mute mode throughout this lecture. If anybody is not able to join, they can go through the YouTube link also, which is posted on the group. Okay, the YouTube link is very comfortable, so there is no point to mute, unmute things. Okay. Sir, it's a request. Just mind if anybody is by mistake keep his mic in a mute, unmute mode, so others should not get disturbed. So I welcome you all the participants, particularly the PG students, as well as some of my dear teacher colleagues from other institutes. So this is the workshop. The main focus of this particular type of workshop is, as my colleagues has already mentioned, most of the students after MSc program go to the pharmaceutical R&Ds particularly, and where the most of the characterizations will be done by the spectroscopy technique only. Moreover, in MSc Part 2, if you see the practical portion, one complete paper is based on spectral interpretation, one complete paper. So the spectrum will be given to you, including the UV, IR, NMR, including C13, sometime DEPT, and mass spectrometer, mass spectra. So out of this all techniques, you have to elucidate the structure of the unknown compound, which molecular formula sometime will be given, or maybe the molecular mass will be provided to you. So on the basis of that, you have to find out the structure of the molecules. So this is the practical portion of MSc Part 2, same 4 particularly. In case of, if you go to the MSc Part 1, there is a complete unit on NMR spectroscopy, and where the structural elucidation is one of the major portion included in the syllabus, including the IR, UV, and mass spectra as well. If you come down to the TY BSc level, there are the technique included this year, NMR spectrometry, as well as IR. So there are some combined problems will be given, and which is similar type of things which we are going to discuss in this particular series of lectures particularly. So the series of lecture will include the basic of the contents, because unless and until you will not understand the basic of spectroscopy technique, it is not easy to understand the concept. I can directly show you the spectra, like if I would say this is the spectrum. Okay, so if I would say, okay, this is the spectrum and you have to analyze it. So it is impossible unless and until you will not aware about the some techniques like UV, IR, NMR, C13, as well as mass spectrometry. So to understand this basic, first lecture, the couple of lectures will be on a basic, and then the couple of lectures will be on solving the problems, which will be in fact given in the MSc practical, same 4. As well as in same 2, you have the combined problems, which will be based on similar type of things. So the TYBSc student will get benefited out of this lecture series, as well as MSc Part 1, same 2, as well as MSc Part 2, same 4 students. In outcome of this, those who have completed their master, they can go to the R&D and they will definitely benefited with this type of knowledge of the chemistry. So I will start with the what exactly the pattern of same for practical. Same for practical includes that spectral interpretation and the project analysis. So the project is completely different, but the one paper is purely based on spectral interpretation. And the spectra will be given to you. First, half an hour will be given to you to interpret the spectra, to read out the spectra. Read out the spectra in the sense, whatever spectral techniques will be given to you, the informations. Kindly unmute your mic, please. Those who are just making a noise here in the lectures. Otherwise, go to the YouTube link if you are not able to handle this instrument. Okay. Now, what I was trying to explain you, the spectrum will be given to you, and the spectrum will look like this. This spectrum includes the first portion is IR. In the corner, there is a UV spectrum. Below, there is a mass spectrum. Then C13 NMR. Then in the last, we have the proton NMR. Now, out of this, the molecular formula sometime may be given, sometime may not be given. So this is the problem over here. You may find out the molecular formula may not be. So from the molecular weight itself, you have to find out the molecular formula too. And in the first half an hour, you have to read out the spectrum with the literature values. That the values will be given in the handbooks. So taking the reference of that, you can just read out the spectrum and note down the values. Sometime the spectrum of UV look like this. There are some values and some concentration values will be given. Sometimes the UV spectrum will be shown like it is transparent. That means it does not show any prominent peak. Or some point they may show you the molecular formula and the other respective spectroscopic technique. And you have to first analyze the spectra in the sense you have to read out, you have to write down the values related to the particular peaks. And then you have to start analyzing that or structural elucidation particularly. As I mentioned in the beginning only, that spectrum may have the molecular formula or may not be having the molecular formula. So how to solve such problems, that we will come to know once you understand the technique. So one by one, we're going to focus on the spectroscopic technique. Exactly. Can you just unmute, please? Purandari sir, if possible. Okay. So this is really a disturbance to the lecture. Now come to the exact point of our interest. That is the spectroscopy technique. There are number of spectroscopic technique which is purely based on electromagnetic spectrum. You all know that those who are targeting the same for practical, they all know the spectroscopic technique. But those who are the beginner like TY or maybe the part one students, for them, I will go slowly. So if you know the electromagnetic spectrum, each bunch of frequencies are having the uniqueness in their energy levels, that they do the specific modification or specific orientation in the structure, organic structure. That if you take any one of the frequency, they have the specific energy levels to do some orientation. Like take the example of IR. So the IR, UV, as well as your microwave radiations, they all are related to the energy levels of the molecules. So that is the molecular energy levels. So each bunch of frequency is related to the one spectroscopic technique. Like take the example of radio frequency, it is related to the NMR spectroscopy. Microwave, it is related to the ESR spectroscopy. IR spectroscopy. Visible, UV visible, that is a UV visible spectroscopy or fluorescence spectroscopy. We have the X-ray, you know, the X-ray crystallography, and gamma rays, it is mass bar spectroscopy. So each bunch of frequencies have their unique energy, and that amount of energy is doing a certain operations in the molecules. And that absorbed frequency will give the certain informations about the structure or the uh, group of molecules or group of atoms together, that is a fragment of the molecules, or we can say the structural informations or the functional group informations will get very clearly with the help of certain techniques. Now, one by one, we will move on to the each techniques. Now, if you see the electromagnetic spectrum, it includes all the spectroscopic techniques. So we will pick a first technique, that is UV spectroscopy. Now, what is UV spectroscopy? The name of this spectroscopy is given by the source. The source which is used for this spectroscopy is ultraviolet light. Now, this ultraviolet light unmute hai. Okay. So this source gives the name of this particular technique. Now, what exactly the UV spectroscopy, that we will see one by one. Now, if you see the molecular spectrum as a whole, the molecule contain different energy levels. If you see here, the first energy level, that is electronic energy levels, and down one, these are the electronic energy levels. So this is a huge gap. If you see here, this is a huge gap. Now, to transit the electron from the ground state to the excited state, it requires higher energy. So the energy of the ultraviolet light is much higher than IR, than microwave and radio waves. So as the energy goes on increasing, the energy levels do certain operations. So like, take the example of electronic energy levels that is related to the UV spectroscopy. If you go to the down one, there is a vibrational energy levels, that is we call as the oscillations of the molecules in terms of the bonds. So there is a vibrational frequency which is related to the transition of the electron from the vibrational energy levels. If you go further down, there is a rotational transitions that is related to the very less amount of energy, that is a microwave, which is in this particular bunch. So I will just take the highlighter over here. So this is your rotational energy levels. These are the vibrational energy levels, and this gap particularly is huge one, that is electronic energy level. So first of all, we are going to focus on these electronic energy levels. Then we will go to this vibrational energy levels, and then further down, this is a rotational, which is not our interest today. Move to the next slide. Just a moment. Okay. Now, what is UV spectroscopy? Now, if you see the molecule as a organic molecules in short, the molecule contains sigma bond, pi bond, and non-bonded electron. Now, the electrons located in the sigma bond, that is a covalent bonded, pi bond, which is a p orbital, which is laterally overlapped, and you know the energy for the sigma bond and the pi bond, how it varies. And there are the non-bonded electron, which is lone pair of electrons lying on the heteroatom, like oxygen, nitrogen, and halogen type of thing, or sulfur. Now, what is the basic spectroscopy technique or any spectroscopy technique? It's the interaction of light with matter. Now, any source, when interact with the light, interact with the matter, some of the light frequency will be absorbed, the energy levels which are quantized, which are matching to the source. There is a transitions, and that for the transitions, the energy will be absorbed from that particular source, and that lines of the spectrum will be missing. So if you see here, a band over here, that is a missing line. That lines have been absorbed for certain operations in the molecules. So this is your, just a minute, I'll take the highlighter. Yes, here. There it is. Okay. Now this is your gap. What is that gap? This is the frequency which is absorbed for the transition of this pi electron to the pi star. So the pi star is non-bonded. This is a anti-bonding orbitals. This is a bonding orbitals. So these bonding orbitals will always have the higher energy level. So when we put some energy to push this electron from ground state to the excited state, it requires certain amount of energy. And that amount of energy will be taken from the light. And which light? Ultraviolet light or visible light. So ultraviolet and visible light have the special operation into the electronic transitions. So the ground state electron will be transit to the higher energy levels. So when we put the energy on this particular orbitals or particular bonds, it transits and it requires amount of energy, and that amount of energy will be taken from this band. This is a band having a different energy levels. So one of the band is missing. That means this missing line is used for the transitions, and that will be detected and computed in the form of the signals, and we will get the informations in the form of certain peaks in the spectrum. And this is common technique for all the spectroscopic technique, which is we use as an absorption spectroscopy. So in contrast to the UV spectroscopy particularly, let's move on to the next diagram. So this is a molecular spectra. If you have any organic molecules, these organic molecules will have certain bonds. The molecule may have the sigma bond, pi bond, or may having the non-bonded electron in terms of the heteroatom. So in all, what we can find over here, we find here this type of possible transition, sigma to sigma star. This is the highest energy transition. You can see from the length. There is a pi to pi star transitions, which is another higher energy. Then there is a n to pi star, which is the least energetic transitions. There is a possibility to have n to sigma star transition as well. So depending on the molecules, like if the molecule is saturated molecules, like maybe the alkane will have normally sigma bond, that is a carbon-carbon or carbon-hydrogen bonds. So mostly they found the sigma to sigma star transitions. If the molecule will have a double bond, that is olefinic double bond, then there is a possibility to have this pi to pi star transitions. And if the molecule is having heteroatom as well as the pi bond, like take the example of carbonyl group. This carbonyl group will have the lone pair of electron as well as the pi electron. So lone pair of electron will be passed to the anti-bonding, which is the particular anti-bonding electron to the pi star states, which is the least energetic transitions. So in the next diagram, you will find most of the things very clear. Now look at here. This diagram is very much clear to you that sigma to sigma star is possible for the alkane, and sigma to pi star is possible, but which is a forbidden transitions. It is possible in case of carbonyl compound, but which is not observed very prominently. Pi to pi star is there. Then n to sigma star is possible in case of the alcohols or halide type of compound. N to pi star, which is the example of carbonyl already we have mentioned. Now there are certain energy levels required, energy requires for the transitions of this sigma to sigma star or pi to pi star or n to pi star transitions. Now here, most of the transitions, most of the electronic transitions in case of the alkane, which is highly energetic, which is possible in the far UV, which is considered to be highest energetic, and normally we don't study such types of transitions in a routine spectroscopy in terms of reading the UV spectrum, because which required a very sophisticated instrument having no air or a vacuum type of instruments, vacuum in the environment of around the instrument. So it is not possible at all, because in the energy levels of 150 nanometers, the air or the surrounding gases may show some type of absorption of this. So most of the cases, the alkane is considered to be the solvent, because we don't study that particular portion of the band. So most of the cases, hydrocarbon or particularly the alkane is considered to be a solvent in UV spectroscopy. Now, most of the possible transitions are that pi to pi star, n to pi star, and n to sigma star, which is possible for lower energetic transition, that is towards the higher wavelength. Now, as I already mentioned, the interaction of light with matter is nothing but what the spectroscopy technique. So this is a source, and this pass through the filter. We call this as a we call prism, which select the frequency considered as a grating as well. And one of the frequency which is tuned for irradiations will be bombarded on the sample, and then the detector will read out which frequency is missing, and that will be computed in the form of the signal. So this is a common technique in terms of the UV spectrophotometer. Now, normally the UV spectrophotometers are double beam spectrophotometer. What does it mean, double beam? That there is a reference as well as the sample that automatically. So in case of colorimetry, we have the single beam that what we do put a cuvette with the water that is a blank, and then we calibrate the instrument, and then we put the sample, and then we do take the reading. But here in case of the UV spectrophotometer, everything is automated. It will take the difference of this, and we can get the directly the absorbance. And that absorbance is because of the absorption of the light by the sample. Like take the example of here. This is the incident light which will fall on the sample. Sample is fitted in the cuvette having the fixed length and the concentration of the sample. And when the light pass through this cuvette, what will happen? You will see the light is dim, that some of the light is absorbed by the samples. So this is a simple logical things which is explained by the Lamberts and Beers, where the more the concentration or the thickness of the material, the absorptions of the light will be more, and which is proposed by the Beers and Lambert, which is well known to all of you, and which is given in the form of the negative log of the absorbed light to the incident light, which is equals to epsilon into concentration into the path length. We will see this equation for calculation of the concentration of the sample. Most of the cases, this particular UV spectroscopy technique is widely used for determining the concentration, because the organic molecules, like structural unit of the organic molecule to determine by UV spectroscopy is not so easy, because there are some other techniques like IR, NMR, which gives the precise informations. But the most important application of the UV spectroscopy is the quantitative measurements of the sample, that is a concentration, which is widely used in the biological study, that is enzyme studies and other things. So we will see what are the applicable things to our spectral interpretation while solving the problems. Now come to the some details things, that the path length of the cuvette is fixed, which is considered to be a 1 centimeter. And if we increase, then there is a linear effect of absorptions, as well as the concentration. As it goes on increasing the concentration, there is a linear effect. The absorptions will be increases, but there are certain limits. Highly concentrated solution cannot be studied with the help of the UV spectrophotometer. There are certain electronic transitions which are having some mixed effect, which gives you the proper information about the structural unit, and that is molar absorbability. Because in the molecules like highly conjugated molecules will show higher molar absorbability, that is epsilon value, and that gives you the very crucial informations for the structural informations that we will see later. Now look at here, some of the solvent used in recording the UV spectrum. Normally we do prefer to use this list of the solvent, where their cutoff value will be given here, that most of the particular carbonyl containing solvents will not be preferred to use as a solvent in UV spectrophotometer, because it do interfere. As I told you, most of the alkane are the compound having like simple molecule like water or isooctane type of thing will be used, like alcohols can be used as a solvent. Move on to the next. Now, what is solvent effect? If you use a more polar solvent in UV spectrophotometer, the more lambda max will be there is a difference between the 20 nanometer in terms of the non-polar and polar. Now, just as an example, I will tell you the solvent effect. If you take a carbonyl compounds in hexane, which is a non-polar solvent, which absorption is 279, which is like 280 nanometer. Whereas in case of ethanol, the polarity goes on increasing to ethanol and then water, which is end up to 265 nanometer. Now, as the lambda value goes on decreasing with the polarity, the energy required for the transition. Now look here, lambda max is inversely proportional to the energy. More the lambda value, lesser will be the energy. That means octane, if we have octane or hexane as a solvent, the N to pi star in case of carbonyl compound, the lambda max value will be higher. That means the energy required for the transition will be less. As the polarity goes on increasing, the push of electron will increases. So this is the brief thing about the solvent. Now, most of the case of the alkane, the sigma to sigma star transitions will be possible, which already we have mentioned. So this is a bonding orbital. This is non-bonded orbitals where the push of the energy from UV will take this sigma electron to the sigma star, which is possible in the far UV region, which is required to be a vacuum conditions. So another chromophores used in case of the study of UV spectrophotometer, like alcohols, ethers, amines, and sulfide containing compounds, where sigma to N to sigma star transitions are possible because there is a non-bonded electrons with the heteroatoms, and which is possible with the lower amount of energy as compared to sigma star. Now, if you see the pi to pi star, which is very much clear in terms of the unsaturated compound like olefinic compound, like compound having the double bonds. So more the double bonds, which is in particularly conjugations, the absorptions of the UV light goes on decreasing in terms of the energy. We will see that in a minute. There are carbonyl groups where there are the two types of transitions are possible. Normally, when we interpret the spectrum, if we get the unsaturation in terms of the carbonyl group, we need to write the two frequencies. One is N2 pi star, which is higher lambda max which is a less energetic transitions, and pi to pi star, which will be less than 285. Like here, in this example, it is mentioned that N to pi star transitions will be possible in the range of what? 285. Now suppose we have here carbonyl compound, and it is mentioned that in the carbonyl compound there is a pi to pi star as well as N to pi star transition. So you have to mention that there is a presence of 285 nanometer lambda max, as well as it may be below that, maybe the 200 or 210 pi to pi star transitions. If that carbonyl group is in conjugation, the epsilon value goes on increasing, as well as pi to pi star transition value goes on increasing. That means energy will go down. So in terms of the pi to pi star transition, if they are highly conjugated, the epsilon value goes on increasing. So epsilon is nothing but the product of concentration as well as the path length as well as the concentration. Okay, so the concentration is related to what? The molar absorptivity coefficient, and which is in simple language related to what? Related to the required energy for the transitions. If there is a highly conjugated system, the amount of energy required to transit the electron from the ground state to the excited state will be lower. So there is a straightaway relation in terms of the molar absorptivity coefficient, that more the absorptivity coefficient, lesser will be the energy, and lesser will be the energy, lambda max will be. Okay, so we'll explain this in terms of the example. Okay, look at here. This is the another example where you can see easily N to pi star will require less amount of energy, whereas pi to pi star requires higher amount of energy. This one is higher energy, this one is less amount of energy transition. So this is up to 200 and this is 285. So this is a basic difference. Now move on to the next. Now, how the UV spectrum looks. Now, UV spectrum is plotted against the lambda max, that is the wavelength, which is measured in nanometer, versus absorptivity coefficient. How much is the absorptions of that particular light takes place? That is, we call it optical density or absorbance. Now here there are the peaks observed. The maximum height of the peak is called as lambda max. The height, that is, this height particularly related to what certain frequency, and that certain frequency is the maximum absorptions of the UV light, and that is the unit of UV spectroscopy, that is lambda max. Normally we do measure lambda max in terms of defining certain transitions in the molecule. Like take the example, there is a carbonyl group present in the molecule, and that carbonyl group shows the lambda max in two levels, that is 285 and up to 200. So these are the two lambda max related to the certain functional group or certain fragments of the molecules. So this is the UV spectrum. Now there are certain effects on the spectrum because of the substituent effects or the environment of that particular chromophore present in the molecules. Normally the chromophores is responsible to absorb the light, and there are some groups which accelerate the absorptions in terms of their intensity, which is we call as a chromophore and auxochrome effect. The chromophore is responsible to absorb the light, and auxochrome is intensify the absorptions, and that intensify as well as the reverse effect will be given by certain effects, and that substituent effects will be shown in this diagram, where if there are certain groups, like take the example of extended conjugation is there in the molecule, the absorption of the UV light will go to the higher wavelength. Higher wavelength, that means that will go to the this side. This is towards the IR side. Okay, so IR is called as what? Red color. So that is also called as a red shift. So that is called as bathochromic shift or red shift, because it is going towards the higher wavelength, higher lambda, and that higher lambda is going towards the IR radiation. That's why we refer this as a red shift or bathochromic shift. That is a shifting of the absorptions to the longer wavelength. Now there are certain effects, or there are certain group which decrease the absorptions of that particular lambda, or we can say the absorptions of the light. So when there is a decrease in the absorptions, that may go towards the UV light. UV, that is a blue color at the end. So that's why it is called as blue shift. This is called as blue shift, or we call as hypsochromic shift. That means the absorptions will go towards the shorter wavelength. That means higher energetic transitions. Requires higher energy. That means it going towards the higher energy level. That means shorter the lambda max. So there is a effect on absorptions in terms of the intensity. That means the chromophoric effect. So chromophore, when it is in conjugation with the auxochrome, like take the example of nitrobenzene, and it is in relation with the like any auxochrome, like take the example of paranitroaniline. So what will happen? The aniline NH2 group will give the electron. That means it intensify the absorptions of the chromophore. What chromophore? The NO2, which absorb the light at higher energy, but it intensify that absorption. So this is called as hyperchromic effect, that increases the intensity of absorptions. So this arrow indicates the hyperchromic effect. This arrow indicates hypochromic effect. This indicates the bathochromic shift or bathochromic effect or red shift. So there are certain groups which decrease the intensity. Suppose take the example of dinitrobenzene as well as your nitroaniline. They are reversed. If you see the compound in the laboratory, you will find that the dinitro compound is considered to be a pale yellow, whereas the nitroaniline are considered to be a dark yellow, because because of the oxochromic effect. So the electron withdrawing group decreases the absorption, so the intensity will goes down. So that type of effect is called as hypochromic effect. So this diagram, if you understand, you can easily narrate what is that effect. Now, more importantly, in terms of the our contrast interpretation of the spectrum is this. Now, most of the cases, the molecular formula will be given, and then you have been asked that so and so frequency will be given. So what type of chromophores are present in the molecules, or what type of transitions are possible in the molecules, or is there any epsilon value? So if we have a chromophore like a double bond, so the double bond, double bond particularly is considered to be a chromophore which is responsible to absorb the visible or UV light. So if you see the one double bond which is isolated, the lambda max will be below 200 nanometer lambda max, whereas the epsilon value will be in thousands. Okay, if there is a extended conjugation in terms of like 1,3-butadiene or diene or trine, the lambda max, particularly for the pi to pi star transitions, goes on increasing. So the lambda max goes on increasing. It means what? The energy required for the transition is less. So these transitions are less energetic, where the epsilon value, particularly the epsilon value, also goes on increasing. Why? Because if it goes on increasing, the chromophoric effect in the solution, the ship goes into the visible range. Like take the example of the beta carotene, where there are 11 double bonds in conjugations, and its lambda max is 465, which is falling in the visible range, where calorimeter can easily study this type of compound. Whereas to study the ethene or 1,3-butadiene or tetrene, it requires UV spectrophotometer. But to study the beta carotene type of compound, the calorimeter itself is sufficient to study the concentration level, because the epsilon value is in lakhs. So more the epsilon value, that means the concentration of that particular solution will be goes on increasing, and ultimately this molecule should have extended conjugation. So in the molecule, if the epsilon value will be given to you in thousands and the lambda value above 200, that indicates there may be the possibility to have extended conjugations. Now, if we have a carbonyl compound, simple carbonyl compound, where that carbonyl compound which is not in conjugations will have this type of n to pi star transitions. For always n to pi star transition, the epsilon value will be very, very less, because it does not show that chromophoric effect. Whereas pi to pi star transitions will have higher epsilon value, because it is responsible for the chromophoric effect. Now, in terms of the conjugated system like alpha beta unsaturated ketone, what will happen? There is a possibility to have both the transition, that is n to pi star and pi to pi star, where pi to pi star transition will have higher epsilon value. That means it going towards the higher the effect of color, the concentration effect particularly. So in the molecules, number of times the values will be given to you. That means like lambda max 280 and 213, and the epsilon value will be like something. So you have to find out what type of transitions are present in that molecules. So the values will be given to you, and you have to find out what type of transitions are present. So the very clever thing in terms of interpreting this value, that first of all you have to calculate the hydrogen deficiency index, like the degree of unsaturation in the molecule, and then some of the chromophoric groups will be easily known to you. Like if you know the IR, if you know the NMR, from the sum of the values you can easily pinpoint, okay, there is a carbonyl group present, that's why the n to pi star value is there, or pi to pi star value is there. So it is interlinked. So just because of the one value or one spectrum, we cannot characterize the whole spectrum. It is interlinked. So you can some point go to the IR, go to the NMR, get some values, get some knowledge about the functional groups, and then comment on the UV. So this is possible. So we will do that later. First, understand the concept. Make sure what exactly the IR spectroscopy and how it is related to the interpretation of the structure of the molecules. So from the UV spectroscopy, you will come to know some of the groups like olefinic group or carbonyl group, their transitions, whether there is a conjugated system or not. So sort of things. But the special type of study is study of the concentration, that is the quantitative measures. Qualitative measure is limited. So we will focus on that later. Okay. So the next slide, I will move on. Just now I have mentioned this slide above one. As the conjugation goes on increasing, the lambda max goes on increasing. Look here. Conjugation goes on increasing, lambda max goes on increasing, energy goes down. Energy goes down. So the energy required for the transition, that means energy required to transit the electron from the ground state is less. So which is explained by this energy diagram. Now, if you see here, this is energy. So ethylene, this is a huge gap. It requires more amount of energy. Butadiene, 1,3-butadiene, energy required is less. Why? Because there is a conjugation. So this energy is less than this. This is only one double bond. There is a two double bond which are in conjugation. Now hexatriene, there are three double bond in conjugation. This energy falls down again. So the energy required for the transition goes on decreasing, whereas lambda max goes on increasing. It's a reverse process. Octatetrene, that means there are four double bonds which are in conjugation. This is the least energetic transition. That means it is more slowly moving towards the visible range. Like take the example of beta carotene, which contain 11 double bonds which are in conjugation, goes into the visible range, that is 400 and something. You know, the UV spectrum will be studied in two scale. UV is studied in 200 to 380, whereas visible spectrum will be studied 400, that is 380 onward, that is 400 to 800 nanometer. So if there is extended conjugation like beta carotene type of thing, you can see here, this is 465 lambda max nanometer. So this will fall in the visible range. Most of the dyes, particularly those who are having extended conjugation, they fall in the visible range. Take the example of naphthalene. If you see the naphthalene in acidic solution, it is a colorless because it does not absorb the visible light. That's why you will get the colorless solution. The moment you add a drop of alkali, that is NaOH or KOH, it turns pink because the moment it react with the alkali, it breaks one bond, and that bonds gives you the extended conjugation and it absorbs the visible light and it gives you beautiful color as a pink. So this is a simple the shifting of UV to visible. I will let you know the best example. You all know Ujala. Ujala we use for brightening of the cloths, which is a chemical. We do add like Neil. Take the example of Neil. We do add in the cloths, and then the cloths looks brighter. The reason behind the Neil or the Ujala type of chemicals, they are the UV light absorber. They absorb the UV light and they emit the visible light. So this is the phenomena, because for the transition, some of the energy will be loose for electronic transition and they shift it to the visible. So when you put the Neil or Ujala type of chemicals in your cloth, so it absorbs the UV light from the environment and they emit the visible light. That means your cloth looks brighter. So this is the chemistry, in fact. Now let's move on to some of the basic slide which is required to understand this UV spectrum. Let's see, for structural determination or structural elucidation, what type of information you require. Most of the time, the compound or the organic molecule will have different chromophores or different oxochromes present, and that oxochrome or chromophore will have electron donating effect or electron withdrawing effect, and because of that, the lambda max value and the epsilon value goes on changing, and that type of thing is really it will show the effect on the absorptions, and that that is not that much required right now, because you will get confused to if you go in details about this, because which is not required right now. Now, just as a example, if you're having a aromatic polycyclic compound, which is a fused aromatic compound, if it goes on increasing the ring size, the lambda max goes on increasing. In from the diagram itself, you can easily pinpoint. So the lambda max, how it goes on increasing. So the more the extended conjugations, or in terms of the annular ring or hetero aromatic ring, so there is a extension or increase in the lambda max. Whereas heterocyclic compound also show the similar type of effect, but they are accompanied with the N2 pi star type of transitions. N2 pi star transitions. Now, come to the actual point. Now, in the first slide, I have shown you the spectrum. That time you may not understand what exactly it is. Now come to the exact point. Now this is a spectra in front of you, and it has been asked to you, read out this spectrum particularly. Okay, this sort of spectrum. This is a UV spectrum, and some informations will be given, and you have to read out that spectrum. You have to write down some of the values. You have to do certain small calculations. So if such spectrums will be given to you, how to read out the spectrum, that I will show you. So which is the actual part now for understanding how to read out the spectrum. So I will get back to this slide again. Okay. Now, okay. Look at this spectrum. First spectrum is this. What it shows, that no significant UV absorptions above 220 nanometers. Now, what you will understand, or what you will comment on this particular spectrum? The molecular formula will be given to you. So the molecular formula is like C3H6O. So before going in details of this spectrum, first of all, read out that is there any olefinic double bond or any degree of unsaturation is there or not. If there is a degree of unsaturation present, then you can easily pinpoint there is a presence of pi to pi star transitions. No doubt there is a oxygen. So that oxygen is responsible for the lone pair of electron. That means it may have N2 sigma star or N2 pi star type of transitions. So you have to read the spectrum. So you have to comment on that particular spectrum. You have to write down some of the values and interpret also. So what you will do first you will take out the degree of unsaturation of the molecules. And you all know how to take out the degree of unsaturation. It's very, very simple. Take out the degree of unsaturation, or we do call this assay, index of hydrogen deficiency. Okay, or index of hydrogen deficiency. That is degree of unsaturation, or we call as the that presence of olefinic double bond, or presence of the double bond in simple language. Now, to understand this type of thing, there is a simple formula that x plus 1 minus y by 2. X is a carbon, y is a hydrogen. So x plus 1 means if you add 1 in the carbon number, so there are 3 carbons. So if you add 1, it will be 4, minus hydrogen, take half, because y by 2 means hydrogen half. So 4 minus 3, so there will be a degree of unsaturation 1. So if you take out from this that there is a presence of 1 degree of unsaturation, that means there is a 1 double bond present. That double bond may be the olefinic double bond, or it may be the carbonyl double bond. You understand? Now, this formula is restricted to if there is a halogen present, or maybe the nitrogen present in the molecule. Then if you see the molecular formula and there is a 1 nitrogen over here, then the hydrogen number will be odd in number. So it may be 5 or 7. So as I told you the formula that y by 2, this number should not be half integral. It should be a complete number. So if there is a nitrogen or halogen, this hydrogen number in the molecular formula will be the odd number. It may be the 5 or it may be the 7. So in that case, from the molecular formula, you have to minus one hydrogen to get the integer number. That means, like suppose this is a 5, and if there is a nitrogen, so you have to minus 1, and then you have to take the half of that if the nitrogen is present. If the halogen is present, again the odd number will be there, so you have to add 1 and then take the half of that and take the difference of carbon number and hydrogen number. You will get the degree of unsaturation. So from this, it is confirmed that there is a 1 degree of unsaturation present in these molecules. Now, if there is a 1 degree of unsaturation present in these molecules, that means you come to know from this structure, there may be the carbonyl group that can be confirmed with the IR values. If there is a value like related to the 1700 something centimeter inverse, you can easily confirm that there is a presence of carbonyl group. So if there is a presence of carbonyl group, you can easily confirm there is a presence of carbonyl group. That means if there is a carbonyl group, that transitions are pi to pi star as well as n to pi star. So if there is a n to pi star transition, that transitions will be up to 280. Okay. If there is a pi to pi star transitions will be up to 200 degrees. That is a nanometer. That is a lambda max. So n to pi star transitions will be 250 to 280 or 290. That depends. If you write here 250 or 260 or 270, nobody will object. But here it is mentioned there is no significant UV absorptions about 220. That means you have to mention this value as a 220. Okay, and this will be 195 or 180. So that means there is no any prominent absorptions like conjugation or extended conjugation. So you have to mention in this spectrum that there is a presence of n to pi star transition and pi to pi star transitions with the lambda max like 220. So 220 you mention here, and this is 195 nanometer for the pi to pi star transition. So this is what the comments on such types of spectrum if it is given to you. So if no significant UV absorption, that means there is an absorption, no doubt, but not significant. That means like there is no extended conjugation or the chromophoric effect. So that's why there is a simple absorptions which is because of the n to pi star, which is not that prominent. That's why it is not shown in the UV spectrum. Now let's move on to the next. Now look, sometime the problem or the UV spectrum will be given in this format. Okay. If the UV spectrum will be given in this format, how to comment on this now? So let me get the pen. Now, this is your lambda max and this is your absorptions. That is an optical density. Now, in the spectrum, you can easily find out by extra plotting over here. This is your lambda max. Okay, but here there are some values given. Now, what is the use of that values? The values for certain reason to calculate the epsilon value. As I mentioned you, epsilon value is related to the concentration term as well as the absorptions. So what is molar extinction coefficient or absorptivity coefficient? It's a product of molecular weight into optical density, into concentration, into the path length. So this is a simple formula of calculation of the epsilon. Suppose this epsilon value is in thousands, like 10,000, 20,000, lakhs. That indicates that this molecule may possess extended conjugation. You have to write the word called as extended conjugation. If this number falls like 10, 20, 100 or 1,000 up to only, then there is no extended conjugation. That is the meaning of that. Okay, so how to do the simple calculations? Now, these calculations are very simple, as molar extinction coefficient is the ratio of molecular weight. Now, where you will get the molecular weight? If you see the mass spectrum, there is a m plus value will be given, and that m plus value is the molecular weight. Okay, so the molecular ion peak will be given in the mass spectrum. That is nothing but the molecular weight of that particular compound. So in this spectrum, 7 to 72 is the molecular weight. So I will write here 72. So this is 72. What is the absorptions roughly? If you see the absorptions, you can calculate. So if you see the middle point, this is 5, 6, 7. So up to 0.7 or 0.8 is nothing but the absorption. So A will be given from this spectrum. So I'm sorry, absorptions will be calculated by extra plotting over here. So you can easily get the absorptions. Okay, so this is your absorptions. So this absorptions is 0.7. So this 0.7 we have calculated. It may sometime vary, like if you extra plot and you are confused. Okay, what is that number particularly? Take the middle of this. That is nothing but the 7.5 and little bit up. So this is your 7. So if it is like if you write like maybe the point 7 2 or 7.5, it does not matter at all, because this does not change at all by such a significant figure. This is not a significant figure at all. So look at the concentration, how to calculate the concentration now. Now the 33.3 milligram per 10 ml. Now how to calculate the concentration? We know the molarity, the gram molecular weight upon the what molecular weight, that gives you the mole in per liter. So this is what our calculations of molarity. Now here 33.3 milligram in 10 ml. So convert into the gram. So if you want to convert this 33.33 into gram, how you will calculate? So 33.33 into, just a minute, I will get the permanent marker. So this is very simple to get. This is 33.33. Okay, just imagine it is going off quickly. So 33.33 into 1000. Okay, and into 10 into again 1000. That means the above value, like 33 into 1000, that value will be something like, I will just show you here, because this is very important to understand why these values are moving not stationary over here. I will just take out. It's moving. Okay, I'll just quickly take out the some other means. Okay, just do it. 33.33 into 1000 upon 10 into 1000 means 10,000. So 33, that will be like this value, this number will be moving here. So what will be the number, like 3330 upon this will be 10,000. So if you take the difference of that, that will be 3.3, and that is the concentration. This is very simple. Just multiply by both this number by 1000, and whatever ratio will come, that is your concentration. Okay, and path length is given 1 centimeter, which is there. So if you do the calculation of this, that will be the 15 number. So if there is a 15 number, that means there is no any extended conjugation. So the concentration I have already mentioned here. So you can easily do this, multiply by 1000 with this number, this also 1000. You will get here, this will be 3, 3, 3. Okay, 0, 0, and 10,000. 1, 2, 3. This will cancel, this will cancel, this will cancel, this will cancel, and this into this will be 3.3. So this is 3.33 is nothing but your concentration. Okay, this is simple way to do the calculation of these things. Okay, good. Now we understand the calculations, and then what now we need to do? We need to comment on this. What need to comment? That there is no extended conjugation. That is our comments. Okay, but this type of mathematical calculation you have to mention in the particular spectrum. So this is what how to read out the UV spectrum. Let's move on to the next. Some point the UV spectrum will be given like this. Now this type of spectrum can be easily now read out by you. There is no problem at all. Like how this concentration can be easily work out just by multiplication of 1000, again 1000, and you will get the concentration. The path length will be changed to this, to this. So you can calculate, because there are the two values given. So you will calculate here, and then you can easily comment on the spectrum whether there is a presence of any extended conjugation or not. Okay. Now, what else? Sometimes the informations will be given in this format. Now this log to the base 10 epsilon, this is nothing but if the value log to the base 10 epsilon value is 3.5 and above. So their epsilon value, normal epsilon value will be in thousands. So if their value is like 1 point or 2 or 3 up to 3, so their value will be up to 100 or just 1000 or 2000, which is not extended conjugation, which is not extended conjugations. But there are 3 different lambda max, which is related to 2 different types of transitions. It may be the n to pi star or pi to pi star, depending on the number of double bonds and the chromophore from the IR, UV, IR. Okay, so such types of spectrum can be easily commented. Like take the example of this, there is a presence of extended conjugation because of 4.2. Whereas this type of compound, which is like 3.5 up to 3.5, there is no any extended conjugations. Here again, the similar type of spectrum, which is already we have commented. So whenever UV spectrum will be given to you in this format, you can easily comment. We will do more practice in actual solving the problem. So just move on to the next slide. Okay, so some of the values you need to understand. Now look here, as I mentioned you that log to the base 10 epsilon value, like 10,000, that is up to 4 and above, which is the extended conjugations value. So that you have to remember. Now here, in case of heteroannular and homoannular, there is a change in the lambda max as well as the epsilon values. So that also you have to take into the considerations, because you know the Woodward's law, and more the substituent across the double bond, and heteroannular link and homoannular, their values are different. So which you have learned in TY-BSc. Okay, so move on to some of the compounds and their values. So just go through this value, we'll get some knowledge. Now move on to the next technique, which is IR spectroscopy, which is very important technique in terms of structural elucidation. Now, what is IR spectroscopy again? Again, the name of the spectroscopy given on the basis of the source used for the spectroscopy technique. Now, here in case of IR spectroscopy, there is a oscillation or vibration of the bonds. So all the organic molecules which is having a carbon, oxygen, carbon, nitrogen bonds present, whether it's a double bond, triple bond, single bond, or whether it's a carbon, oxygen, or carbon, hydrogen, all types of bonds have their own energy of vibrations. They all have natural tendency to vibrate like a spring. We all know the spring. So like the spring, they do vibrate, and each of the bond will have their fixed amount of energy to vibrate. It requires fixed amount of energy to vibrate. So picking that point in considerations, and back to our first molecular spectrum, that if you see here, that UV spectrum required this much gap of energy, that huge gap of energy, that means which is higher energetic transitions. Whereas in case of vibrational transitions, the energy required is very less. So from this to this or this to this. So there are some overtone band too. So this is normal bands and this is overtone band. So max to max required is very less as compared to the UV visible spectrum. So if you see here the source, which is exactly next to the UV visible, that is a least energetic than UV visible source. So the source which is used here, IR, and the energy required for the transition is again less, and that amount of energy is exactly match the oscillation or vibrations of the bonds present in the organic molecules, like carbon hydrogen or carbon type of vibrations. So this type of vibrations normally are of different types. There is a symmetrical stretching or symmetrical stretching, bending type of vibrations. So the basic things for the IR or selection rule for the IR spectroscopy is what? That molecule or that compound should have a fixed dipole moment. Okay. If the dipole moment is there, then and then the molecule will be able to do the absorb the particular type of IR radiations. Now that particular vibrations are of different types, as I mentioned. If there is symmetrical vibrations, like if one atom is bonded with the two things which pulling that particular central atom in equal energy, so the net result will be zero, and such types of molecules will do not absorb the radiation. So there should be a dipole moment in the molecule, and that is the selection rule of IR spectroscopy. Now, if you move on to the again the electromagnetic spectrum, you can see here UV visible and then IR will fall. If you go towards the radio frequency, there is a lower energetic transitions, and if you go towards the gamma rays, you know that higher energy transition. So we are going to move towards the lower energetic transition, that is the higher lambda. But this time we're not going to use a lambda which is in terms of 250 to 15,000 nanometers. So instead of that, we do convert that lambda into the wave number, and that wave number is the reciprocal of the your lambda, and that is measured in centimeter inverse, and which is having a band of 900 centimeter inverse to max 400 centimeter inverse, but the functional group falls up to 3600. So most prominent bands will be from some point there is a peaks in the range of 600 also. So 900 is a standard thing, but it may go down in the fingerprint region up to the 600, because there is a cis and trans transitions which falls under the 690. So these values may go down. So more the standard spectrum of IR will falls in the range of 600 to 4,000 centimeter inverse. This is what the range of IR spectrophotometer. Now look at here what exactly the IR spectroscopy technique. Now if you see here a bond between the two atoms, they are flexible, they have the natural movement like a spring, and they do vibrate, and they have a fixed dipole moment. If there is a dipole moment, then obviously they have the difference in the energy produced by that particular vibrations. If the energy is same, so there is no possibility to couple the vibrations of the incident light, and that will not match at all. We will see that in the next diagram. Now look at here, all the molecules, organic molecules containing the covalent bond particularly, they all have a spring-like vibrations, and that spring-like vibrations have the fixed amount of energy. All carbon-carbon or carbon-oxygen or double bond, triple bond, wherever you come across with the bonds, they all have fixed amount of energy to vibrate. So this is the concept. So if you see the molecules particularly in a whole, like take the example of phenol. Phenol will contain the prominent like bonds like carbon carbon double bonded, carbon oxygen, and oxygen hydrogen. So in the whole molecule, the oxygen and hydrogen bond is unique over here to have some different types of dipole moment, and which peak will give you the very sharp peak in the IR spectrum. No doubt other bonds will also give the peak, but they will found a bunch of peaks together, and that we have the another applicability to read out or to have the information related to the structure, that is a fingerprint region. We will see one by one. Now look at here, there are different types of vibrations. As I told you, there is stretching vibration, there are bending vibrations. So this is the diagram here. We can see here these molecules. This is a symmetrical stretching where both the bonds are vibrating in same motion, whereas in case of asymmetric stretching, there is a change in the dipole moment, and such types of molecules are easily show high energetic vibrations which absorb the IR radiations in the higher energy band and show the absorptions of the frequency, and we will get the peak. But in case of UV, IR, and the UV. In case of UV spectroscopy, we have learned about the optical density, that is absorptions of the UV visible light. Whereas in terms of the IR spectroscopy, we do learn percentage transmittance, and that percentage transmittance makes the IR spectrum completely different than the UV visible spectrum. We will see that in a minute. Now look at here. What we have learned here, that there are two different types of vibrations, that asymmetrical stretching, which is highly energetic vibrations, whereas bending vibrations are least energetic vibrations, which are of different types. In plane vibrations, out of the plane vibrations like scissoring, rocking, twisting, wagging. So all these are the bending type of vibrations, and the bending type of vibrations require very low amount of energy, less amount of energy as compared to the asymmetric vibrations. Let's move on to the next diagram. Now look at here. This diagram indicates the spring type of vibrations of the molecules will produce this oscillation, that is a fixed amount of energy. Now this is an oscillation produced by means of this bond, and this is having a certain amount of energy. That is we can call it is a induced field. It is a produced field by means of this the stretching of this bond. So stretching of the bond produces some energy, you can say, and that energy looks like in this format. Now if you move on to the actual spectroscopic technique, what is a spectroscopic technique? The light, incident light falls on the matter, and the matter will absorb the light, and then some of the lines will be missing, and that will be computed, and we'll get the signals. So in the same fashion, now what will happen? This particular we can say vibrations will be in this way now. Now look at here what I have put together. This is a vibrating bond, produces this amount of energy. Now I incident the beam of IR radiations, which is having the similar type of energy. Now look, now when, as I told you, the energy levels are quantized. What is the meaning of that? Quantized energy level means the energy of the energy of the incident light and the energy of the bond, when they match, there is a resonance. That is a resonance, and that is the equal energy states. Now when the beam of energy having the bunch of frequencies of IR, when falls on the molecules containing the induced magnetic field or induced field, which is produced by means of the vibrations of the bond, they do couple. This is a different frequencies now. We are focused here only one bond, but in the molecule there are number of bonds which vibrate at once, and they produces their field, and the incident beam will have different frequency, and each one of them will match and they couple. When they couple, that means the energy which is incident on the bond will absorb the coupled waves. That means that energy will absorb, and that coupled wave will be missing in the detector. And that means in the previous slide I have shown you, the missing line will be computed and will be converted into the signal, and that signals will be shown here in terms of the spectrum. And the spectrum is plotted the wave number versus percentage transmittance. Now look at here, if the sample is transmittance, means 100% like it is not responding to the IR radiations, that means there will be a straight line, there will be no absorbance. So that means 100% transmittance means no absorption. Like take the example over here, this 1998 over here, I would say. So here there is a like something 95 type percent or 92% percentage transmittance. That means there is no absorptions. So when there is a less percentage transmittance, like maybe the 15 or 10, that means there is a maximum absorption. So this peak, the prominent peak, or this particular peak, which is having absolute absorption, like maybe the 100%. Now this is zero transmittance. That means what? 100% absorptions. So this is reversely, exactly inversely proportional. So this spectrum is versus percentage transmittance. That's why these peaks are exactly opposite to that of your UV spectrum. Normally the absorption spectrum will be look like this, okay, and the emission spectrum look like this. So this is percentage transmittance. So this peaks looks like a reward. And here the short peak, that means like bump, this is a small hump over here. That means there is a maximum transmittance and less absorption. That is a simple meaning of this spectrum. Let's move on to the next. There are different types of spectrum, like strong absorptions. What strong absorptions? Like there is a transmittance is low, that 0 to 35. Medium is 35 to 75. And weak is what? 90 to 75. That means if you see in this earlier spectrum, these are the weak absorptions. Here, this is a strong peak, this one and this one. So these all are the strong absorptions, these peaks, and this or this particularly, they are weak absorptions. So this is a simple meaning of this particular spectrum. Now, this is what we have mentioned over here. Now look at here, how the spectrum will be given to you. Now there are the two types of the spectrum, or two categories. There is a functional group detection or functional area, and another one is fingerprint region. Below 1000 or 900. Okay, so this particular area fall under the fingerprint region. You know the fingerprint region, the any molecules which is having a fingerprint region sort of this will never ever match to any one of the molecules. So this is a unique identity like a human being. So our fingerprint will never ever match, and this become a forensic tool for the criminal investigations. Like that, the molecules will have a fingerprint region very much unique for their own identity. So this tool can be used for the identification of the structure of the molecules directly. If we have a gallery of the standard spectrum, we can match it and we can easily confirm which is the structure. But our interest is to learn the functional group region. This one, this is we call as functional group region, where the prominent peak will be shown, and that prominent peaks are because of the prominent functional group. Like take the example of CH bond or NH bond or OH bond, or maybe the triple bond, double bond, and single bond. So all that functional group will fall in the functional group region. Okay, so let's move on to the next spectrum. Quickly, we will take a major portion from IR, and then rest of the things we will move on to the next lecture tomorrow. So if you see here broadly, the OH, NH, and CH peaks will fall in the range of above 3000. Triple bond, acetylene and triple bond of nitrile compound will be in the range of 2100 to 22. And double bond in terms of the carbonyl and maybe the amino group, and particularly the double carbon-carbon double bond will be in the range of 1700 to 1600. Or moreover, it may be the up to 18 to 1600, which is a prominent for carbonyl region. And this rest of the peak is considered to be fingerprint region, and which is a unique tool for the identification. Now, this is one of the simple thing, like the reduced mass is inversely proportional to the wave number. Like take the example of halides, like iodide. If you see the carbon halide, that is a iodide stretch, which is less as compared to the bromide, chloride, which is related to the reduced mass. And here the oscillation frequency, that is the frequency of the bond vibrations as well as the incident light, is directly proportional, and which is related to reduced mass of the compound as well. Now, some of the stretching frequencies are given here that you have to practice to know some of the common frequencies. Like as I mentioned you, some of the groups like OH, NH, or CH, they will be above 3000, and then this triple bond will be fall in the 22 or 2100. Carbonyl compound or double bond like about 1600 to 1800, and then rest of these your bending vibrations. So sort of things, you if you practice, you will understand which peak is belongs to what type of functional group, because This IR spectroscopy is also called as functional group detection spectroscopy. This is called as functional group detection spectroscopy. Why it is so? Because each of the molecule will have a proper functional group, and that proper functional group gives you the unique information about that particular structure. So there are some of the olefinic compound, like take the example of cis and trans. They have the unique stretching frequency or bending vibrations, I can say. So if we have like this is take the example of trans vibration, which is 960, which is unique. If it is a cis, then it will be 660 or 690. So these are the two values which are very much important to distinguish between the geometrical isomerism. So there are certain values which are monosubstituted aromatic ring, disubstituted, and their stretching frequencies are given over here. If you know this frequency, you can easily comment on the compound, which is whether there is a monosubstituted or disubstituted, and you can easily characterize the molecule. Now let's move on to the next slide. So some of the things, how the OH peak is broad and this peak is sharp. The reason behind the exchange of this active proton. So this proton is very much active to replace with the impurities in the sample, and that's why these peaks are broad. There is a carboxylic group of carboxylic OH group, which is very much hugely spread across the spectrum, which is in the range of 2,500 to 3,000. So such a big broad peak is there for the OH of the carboxylic group. Number of times the NH2 and NH will be distinguished between the doublet and singlet. Suppose this is a secondary and this is a primary, it can be easily pointed out. So there are some peaks which are aromatic CH straight and olefinic CH straight, which are above 3,000, and you can easily comment on the structure that this particular peaks are from the aromatic CH straight. There is a sharp peak of carbon hydrogen straight of the acetylene. So this particular is possible in 3,300, which is always confusing in terms of the OH and NH peak. But this is a sharp peak which is 3,300 centimeter inverse. Now there are certain effects on the stretching frequency because of the conjugations. If there is a extended conjugation with the aromatic ring, the stretching frequency will fall down, the energy required will be less. Whereas if there is a isolated carbonyl group, the required frequency will be less, required energy will be more, that is 1715. That is a higher higher wave number, that means higher energy. More the wave number, more will be the energy. We have seen in the earlier slide, there is a direct relations between the oscillation frequency and frequency absorbed. So if there is a conjugation, the energy of absorption will be less, and this is because of the extension of the conjugations. Now there are certain groups which is showing the positive inductive effect and negative inductive effect. If there is a positive inductive effect, the group which are electron donating, they affect the carbonyl stretching frequency. More the electron donating group, so lesser will be the stretching frequency, and the stretching frequency occur at lower amount of energy. Whereas electron withdrawing group increases the stretching frequency because there is a strain on the carbonyl group, and ultimately the stretching frequency will goes on increasing. Let's move on to the next slide. Now already we have mentioned here, there is a no doubt conjugation, but there is a substituent effect also, that is a steric effect. If this double bond is having a substituent, so the value of substituent will also affect this stretching frequency of the carbonyl group, which is increasing. The strain in the ring, the 5-member, 6-member, 7-member, and 3-member ring. So the carbonyl carbon will have high strain, and high strain will increases the stretching frequency, and ultimately the stretching frequency of this 3-member ketone will high as compared to the 5-member. So as the strain, wear strain goes on increasing, the stretching frequency also goes on increasing because of the change in the bond angle of the sp2 hybridized carbonyl carbon. Some of the hydrogen bonding as well as the sterically hindered group also affect the stretching frequency. Carbonyl stretching frequency, the hydroxyl group, which is on aromatic ring, will also affect because of the hydrogen bonding, the intramolecular hydrogen bonding as well as the intermolecular hydrogen bonding. So there are certain groups where the carbonyl stretching frequency as well as in conjugations will be given here. So you have to just look into this frequency, go through this frequency. It will be helpful while solving or while interpreting the values. So these are the list of frequencies which are required to be known to you. Now, suppose this is the IR spectrum, and this IR spectrum is giving showing some of the peaks, and you have to interpret like below 3000, the peak is related to the carbon hydrogen stretch of the alkyl group. It may be the CH2, CH3, or CH. So wherever you come across with the peak in the range of above 3000, that is aromatic CH stretch. Below 3000, that is the aliphatic CH stretch. That is aliphatic means methyl, ethyl, or methylene. That is CH stretch. If you're having a 1700 something peak, that is a carbonyl stretch. It may be the aldehyde or it may be the ester, depending on the molecular formula. You can easily comment out. Suppose this is your vibrations, which are bending type of vibrations, maybe the scissoring, rocking, and need not to mention each and every frequency, because some of the frequencies are in the bending and which are not precisely mentioned. Some of the time the frequency is in the range of 1200 to 1100, which is carbon oxygen stretch of the ether. If the ether or ester will be given, that frequency will be coupled with that. So that you have to look into. While solving the spectrum, we can easily comment. Like look at here. This is the compound where there is aromatic CH stretch that is above 3000. That is aromatic CH stretch. Below 3000, there is a CH stretch of alkyl group, that is a CH2, CH3. There is a 1726 CH carbonyl stretch, which is of carbonyl of ester, which is in conjugation. That's why it is 1726. Otherwise, this value will be 1740, 45. Now here, this is in conjugation. That's why the carbonyl stretching frequency will be goes down. Here, this is a ester. So there is a ether as a carbon oxygen stretch, which will be there in the 1100 or sometime 1200. So this is the interpretation of the spectrum. What interpretation? That carbon hydrogen stretch of the aromatic, alkyl stretch, carbonyl stretch, and these are the carbon oxygen stretch and the bending vibrations. Suppose we have a toluene here. There is a carbon hydrogen stretch, there is aliphatic CH stretch, and all these are the double bond. That is a 1500. This is a 1500, 1400. These are the double bond stretch, which are of the aromatic ring, and the rest of the things are the carbon hydrogen, carbon stretch of the bending type. Now look at here. This is the spectrum. Now this is an unknown spectrum. What you can comment on this? Now look at here. This is 2960. That means this is aliphatic carbon hydrogen stretch. That means this compound may possess carbon hydrogen stretch of maybe the CH3, CH2, or CH. There is a value related to this, that 1500 something or 1100, 1200 something. But these values are not prominent because 1200 and something. But here, this value is of olefinic double bond or maybe the double bond of the aromatic ring. Suppose there is a 1760 or 1650 values, there is a presence of double bond, which is it may be the cis or trans. If you know the value, just now we have mentioned that cis value will have a lower value as compared to the trans geometry. So this you can easily comment out from the IR spectrum. Look at here. This is another spectrum, that is 1686. It is related to the carbonyl stretch, which is in conjugation. It may be the amide or it may be the extended conjugated carbonyl group. This is below 3000. That means alkyl group is there. Above 3000, there is a maybe the aromatic CH stretch, and there are certain fixed values over here, not mentioned here, but there are some values of the carbon double bond, maybe the aromatic or olefinic. There is a value related 1200. If there is a carbon oxygen stretch, you can comment on that. Need not to comment on each and every value. Those who are prominent value like this one, you can comment on that. Now, this is all about the UV and IR spectroscopy. So in the next lecture, probably maybe tomorrow, we will comment on the PMR and CMR, and then we will move on solving the problem. Also, we are going to talk about mass spectroscopy. Once you understand the technique, you can easily comment on the different spectrum, particularly for the analysis point of view. So this is all about for the day. So we'll stop here because it is more than 1.5 hours. So we will continue in the next lecture. and everything will be commented in the WhatsApp group. So link and the YouTube link will be shared. So thank you very much indeed. So we'll stop here. Hope my colleagues is there. If not, I can stop you because this is live in the YouTube group.
Okay, sir.
I don't want anything unwanted things. So we can conclude, sir, over here. Purandare, sir, we will continue tomorrow.
Okay, sir. Tomorrow we'll continue.
Yes. So thank you very much, guys, for patient listening. We will